In this video, we're going to learn the names for several special kinds of polar function graphs. Okay, so I do want to preface this by saying you don't have to memorize all of the requirements or conditions that lead to each type of graph. All I want you to be able to do is just maybe look at a picture and recognize, oh, I've seen that shape before. So if I talk about a limacon or a cardioid or a rose curve or something, you can at least know what that term means. Again, you don't have to memorize, is this when a over b is less than 1, etc. Those things are not important for this course. I just want you to be able to look at a picture and say, oh, okay, I've seen that shape before. That's a limacon, or whatever. Okay, so let's look at those special shapes we're going to see. Okay, so these are all called limacons. So they're like a circle, but they've got some amount of a little dimple there. Okay, if it doesn't actually dip in and it just kind of flattens out, that's a convex limacon. If it does start to dip in, but it doesn't get to a point, like this, it's called a dimpled limacon. And if it looks like a heart, then it actually comes from this word heart appearance, cardioid. Okay, so we call that a cardioid. And if it gets so far pushed in that it actually loops in on itself, then we call that a limacon with an inner loop. And this little guy right here is the inner loop. Okay, so again, don't worry too much about that. Just be aware these things are all called limacons, but also if it comes to a point, we can call that more specifically a cardioid. Okay, another kind of shape we might see. In our last example, we looked at a rose curve with 3 petals. Okay, you could have tons of different numbers of petals, right? We could have, this looks like 8 petals, 5 petals, 4 petals, who knows? Okay, so if we have an equation like this, cosine of n theta or sine of n theta, turns out there's patterns to figure out how many petals there's going to be, but again, you don't have to memorize those things. Okay, so just be able to recognize if it looks like kind of a spirograph drawing of a flower, great, that's a rose curve. Okay, now some other interesting ones we can get. Sometimes we could end up with a circle, either off to the right, maybe the left, to the top, maybe the bottom, or we can end up with these 8 or infinity looking shapes called lemniscates. Now what makes lemniscates a little bit weird is that if you notice, these equations aren't actually given in terms of r, they have an r squared. So if you were to try to solve that for r, it would actually be 2 equations. So this would be a times the square root of sine 2 theta, and negative a times the square root of sine 2 theta, for example. So all the stuff we learned about those shortcuts for symmetry, that works if it's just r equals, but if it's r squared equals, then we've got a weird square root there, kind of all bets are off. So lemniscates are a little bit strange, but just be aware you can end up with a figure 8 shape like that, but it is going to require that you have an equation for r squared, or really just 2 different equations for r. So what we're going to do now, since we've learned about the names of each of these shapes, is we're going to try to go ahead and sketch a lemniscate. Okay, now we kind of had a warning this would be a lemniscate because I've got an r squared equals. That's the only thing we've seen that's like that. Okay, so we're going to use the same steps we used before. Now I can't rely on any shortcuts for the symmetry here. Okay. So that's because I don't just have an r equals, I have an r squared equals. So let's go back to everything we learned about symmetry. I could try plugging in any of these 3 combinations. R comma pi minus theta, r comma negative theta, or r comma pi plus theta. The only one of those where if I did that it would work out is this last one. So let's see that in action. Okay, so again, I'm just going to plug in pi plus theta for the angle. Okay, let's see what happens there. Okay, now if you add 2 pi to anything and plug it in a trig function, nothing's going to change, right? That's just the period of any trig function is going to work with 2 pi. So this is the same as 9 sine of 2 theta, which, as it turns out, is the original equation. So that does confirm that I have polar symmetry. In other words, once I have some points, take each of those points and shoot it to the other side of the origin, you'll have another corresponding point there. Okay, so let's see if we can plot some points then and figure out what this graph is going to look like by the end. Okay, so let's get a little table of values to plug in. And I'm not even going to have to plug in that many. Let's start with 0. Okay, so the sine of 2 times 0, that's just going to be 0. So I've got 0. Okay, not so bad. Now, okay, so this is r. When you take the square root of it, it's just going to be 0. Now here's where things get a little bit different. Let's work with some numbers that are not 0. So pi over 12, if I double that, that's pi over 6. Sine of pi over 6 is 1/2. So 9 times 1/2 is 4.5. Okay, so let's talk about what's going to happen here. Okay, so that is, oh, hold on. Yeah, okay, that's right. That's r squared. Okay, so if I want to actually go back and find r, I would need to take the square root of that. Okay, now I'm not really too concerned about simplifying this. If I put that in my calculator, it's going to be just a little bit bigger than 2. Okay, so my r values are going to be a little bit bigger than 2 and a little bit smaller than 2. Let's get some nice exact values there so I know what to work with. What is the square root of 4.5? Roughly 2.1. Okay, so I'll have two different values here, 2.1 and negative 2.1. Let's keep working with this. Okay, what about pi over 4? So if I plug in pi over 4, alright, I'm going to double that. That would be pi over 2. Sine of pi over 2 is 1. So 9 times 1 is 9. So if r squared is 9, r is either 3 or negative 3. Let's go ahead and just graph what we've got so far. Okay, so I'm starting with an angle of 0, a distance of 0. Now, when I go out to an angle of pi over 12, that's this direction, I'll either be going out 2.1 or 2.1. Okay, so I'm going this way, or I'm also going that way. Alright, let's keep going. When I go out to an angle of pi over 4, okay, so that's about there, I'm going to be going out a full distance of 3, so 1, 2, 3, or a full distance of 1, 2, negative 3. It'll look something like this, right? I'm going out in two different directions at once because one of them is positive, one of them is negative. Okay, let's keep working with this. 5 pi over 12. If I plug in 5 pi over 12 and double it, that's 5 pi over 6. Okay, the sine of 5 pi over 6 is 1/2. Okay, so 9 times 1/2 is 4.5. So if I take the square root of both sides, r squared is 4.5. That means r is, well, we did this before, 2.1 or negative 2.1. Okay, so let's look at that. 5 pi over 12, that's right here. So here's 2.1, and in the opposite direction, here's negative 2.1. Okay, and there's nothing magical about these numbers I chose to plug in. I'm just picking some numbers so I can get a feel for things. Now let's try pi over 2. So pi over 2 times 2 is pi. The sine of pi is 0, so this is right back to 0, which means r is just plain old 0. So this one comes in, and this one comes in. Okay, and that's it. So if you think about the symmetry, each of these points is supposed to have a corresponding point on the other side. Well, we actually have already seen that happen. I don't need to add anything else. This one corresponds to this one. This corresponds to that. This corresponds to that. Okay, so that symmetry has already happened here, just reflected to the other side of the origin. And at this point, I could keep plugging in more points, but I'm just going to keep tracing this weird diagonal figure 8 shape over and over again. Okay, so this is just an example of a lemniscate. I strongly encourage you, since we're going to have our calculator available for every test, even though it's useful for us to be able to graph these things by hand, and I may request it sometimes, always just go back and double check yourself on the calculator. Make sure your graph looks right. Right, so as soon as I'm finished here, I just want to make sure, okay, did I do this right? Now, if I go to plug this in, I have to be a little bit careful. I can't just type 9 sine 2 theta. That's not what r equals, that's what r squared equals. So let's take the square root of both sides. I mean, r is plus or minus the square root of that. In other words, plus or minus 3 times the square root of sine 2 theta. So I'm going to have two separate equations if I want to double check this. Okay, so I'll have 3 times this, 3 times the square root of the sine of 2 theta. Or, I can have the other version, that's negative 3 times the square root of the sine of 2 theta. Okay, and you do want to make sure that you're in radian mode. That can be really important. Okay, so let's look at that graph now. So there it is. There's that kind of diagonal looking figure 8 shape. It's exactly what we just graphed. Okay, so just be aware, lemniscates are a little bit strange because they're not solved for r. It's almost like conic sections, how they're not solved for y yet. If you need your calculator to do that work, just start by solving for r and then it'll know what to do.